Hello world, Joshua here at JTC Education, and this is the maths of juggling. Okay, so our exploration into the mathematics of juggling begins with vanilla site swaps. A site swap is simply a name given to a mathematically juggleable pattern. The reason they're called site swaps will become clear shortly. For now, we're just going to look at vanilla site swaps, which are kind of the bog standard juggling pattern, and they are juggling patterns within which no more than one ball can land in one hand at any given time. Just to make that point a tiny little bit clearer with two balls, this would not be okay in a vanilla site swap, two balls in the same hand at the same time. This, absolutely fine. At no point were both balls in the same hand at the same time. Let's go onwards. So in order to be able to write down the mathematics of juggling, we need to firstly split time into beats. And a beat is simply the time between each throw. Indeed, you can see in these diagrams here, I have hands right, left, right, left, right, left. And if I draw down here, this is my time axis. And so each throw, right and then left, is separated by one beat. And it's important that we understand that a beat doesn't have to be 1 second. A beat can be any unit of time that we wish it to be. Indeed, if a beat is very short, then it means I have a very low juggling pattern. And if a beat is very long, I have a much higher juggling pattern. Now I'm going to go over to my long-lost brother in Rio de Janeiro, Hasoj, and he's going to demonstrate this point with some real-life examples. Over to Hasoj. Hasoj here, Josh. Ready to juggle. In this juggling pattern, we can see that Hasoj is throwing the balls high in the air, and therefore the beats are long. Now, whilst this is exactly the same pattern, Hasoj is throwing the balls very low this time, and therefore the beats are short. Now let's talk about the different types of throws we can make. We could make a one-beat throw, and a one-beat throw is effectively a pass. Let me show you why on the juggling ladder diagram. If I throw a ball and catch it one beat later, then no other event, no other throw has happened between that beat, right? I've just gone from right to left in the space of one beat, so effectively I have passed the ball. Okay, what about a 3-beat throw? Well, for a 3-beat throw to work, I must give it at least a little bit of height. If we look here at my diagram again, and I'm throwing from my right hand, and I count 3 beats, 1, 2, 3, we can see that it starts at right and it ends at left. However, the difference with the 3-beat throw is there have been 2 throws in between, namely one throw with the left hand and one throw with the right hand. So in order for that to be possible, there must be some height to the throw such that my right hand and left hand can make 2 throws underneath it. And now let us ask about a 2-beat throw. Well, 2-beat throws are quite interesting because it means I would start, for example, with the ball in my right hand. I would count 1, 2, and it's back in my right hand. And the only thing that happened between this throw is something with my left hand. So effectively, for a 2-beat throw, I could just hold the ball because the only hand that's going to do something whilst I'm holding it is the other hand. I could give it a little throw if I wanted to, but I don't have to. So at this point, you might like to see if you can spot a pattern between all even beat throw numbers and all odd beat throw numbers. Indeed, any odd beat throw number will always land in the opposite hand, because if I start in the right hand and I count 1 odd, 2 even, odd, even, odd, even, odd, if it's an odd throw, I will always end up in a different hand to which I started. And if it's an even throw, even, I will always end up back in the same hand. So now that we've defined what each throw is, we can try and write down a sequence of throws which can be juggled. In other words, no more than one ball will arrive in one hand at any given time. Let's start with a 3-ball sequence, and the simplest one we can juggle is 3, 3, 3, 3, 3. So remember, if I'm doing a 3-ball juggling pattern, I'm starting with 2 balls in my right hand or 1 ball in my left. So let's draw those in for starters. 1 ball here, 1 ball here, and 1 ball here. And I'm going to throw a 3-beat throw. So this is going to go 1, 2, 3 and land here. This goes 1, 2, 3 and lands here. And 1, 2, 3 and lands here. This is really promising because at no point has any ball landed at the same time in the same hand. And indeed, we are now, after 3 throws, 1, 2, 3, we are back to this ball which was recently caught by the left hand, and this can make another 3 throw. And then this right hand, which just called a ball, can also make one. This can make one, so forth. And we can continue ad infinitum, and what we have effectively written there is the juggling pattern 3, 3, 3, 3, 3. When we notate a juggling pattern, if we have a repeating unit, like the number 3 here, we can abbreviate this just to 3. So this is the juggling pattern 3. It was with 3 balls. Remember, there was one here, and one here, because we started with 2 balls in the right hand and 1 ball in the left. And we have proven, because no more than 1 ball ever leaves a hand at a time, and no more than 1 ball ever meets a hand at a time, that it is a juggleable vanilla side swap. And you may have already noticed that this is exactly the pattern that Hysaj was juggling before. So just to tie this in with the juggling ladder diagram, indeed we notice in this pattern the balls are always changing hands, and every time a ball is thrown, there are 2 more throws made before that ball comes to be thrown again. Okay, let's find another pattern. What about if I start with 2 balls in my right hand and 1 ball in my left, just like last time, and this time I throw a 4-beat throw. 1, 2, 3, 4. So this ball will land 4 beats later. And then I throw another 4-beat throw. Okay, it's back to the same hand we discussed already. Even number throws return to the same hand. And then let me throw a 1. Well, at the moment, this looks promising. No line has met with a hand at the same time as another line. Let's see if I continue this, if it is still promising. So I've made 3 throws. 1, 2, 3. I'm now here. I've recently caught a ball, and I'm going to throw another 4. And then I'm going to throw a 4 from here, 4, and finally another 1. This is still looking very promising. Let's do one final round of 4, 4, 1, just to triple check. So I've made 1, 2, 3, 4, 5, 6 throws so far. I am here. I've just caught with my right hand. I'm going to throw a 4, then my left hand is going to throw a 4, and my right hand throws a 1. And we can see that there is no line, no 2 lines that meet with one hand at any given time, and there are no 2 lines emerging from one hand at any given time. And therefore, 4, 4, 1, 4, 4, 1, ad infinitum is a juggleable pattern. The repeating unit is 4, 4, 1, and therefore we can just notate this as 4, 4, 1.
Got it, Josh. 4, 4, 1.
Just notice here how the 2 4 throws return to the same hand, and the 1 is passed from right to left or left to right. And here's Hysaj performing the very same trick at full speed with clubs. Great, so now that we're all becoming professionals at drawing what we call juggling ladder diagrams, let's have a go at drawing on the throws for this pattern, 5, 3, 1. So, load up my balls, 2 in the right hand, 1 in the left hand, and I'm going to throw a 5 throw. 1, 2, 3, 4, 5. It lands 5 beats later in time. Then I will throw a 3 throw. 1, 2, 3. Lands 3 beats later in time, and I will throw a 1 beat throw. Bingo. Looking very promising. No 2 lines are meeting one hand at the same time. Let me just draw one more round in for us. So we're up to here. I'm going to throw another 5 throw because I'm at the beginning of the sequence again. I'm going to throw a 3 throw and a 1 throw, and I could continue this once again ad infinitum, and therefore 5, 3, 1 is a vanilla side swap pattern. 5 is the high throw, the 3 is the middle throw, and the 1 is the pass. Awesome, so now we're ready to see where the term side swap comes from. If I write out my simplest 3-ball pattern, which was just 3, 3, 3, ad infinitum, let's explore what happens if I try and swap the site of 2 of these numbers. Well, if I want to bring this throw and make it 1 beat earlier, I had better throw it 1 beat higher so that I can guarantee that it still falls at the same point in time. So I'm going to bring this 3 down here, and it's going to become a 4. Okay, and remember, this 3 was throwing 1, 2, 3, and the 4 is going to throw 1, 2, 3, 4. They both land at the same point in time. So I know for a fact this is all good, so long as at the same time as doing this, when I bring this 3 here, remember I'm swapping the sites of these 2 numbers, I take away 1. Why? Because I'm throwing it a beat later, therefore I must throw it a beat, 1 beat less high in time. So I've swapped these 2 3s. As this number comes down here, It increases by 1 as this number shifts to the right, it decreases by 1, and I have a new juggleable site swap, 423. Hussage, let's see it. So the 4s are being thrown to the same hand, the 3s are crossing hands, and indeed the 2s, which are holds, are being held in the air. Thank you, Hussage. Okay, I've got a challenge for everybody now. I wonder if you can make another swap of two numbers to get to the pattern 441, which we have already seen over here. If you fancy giving that a go, pause the video right now. Well done if you figured out that you need to swap these two numbers to arrive at the pattern 441. Indeed, as I shift this 3 to the left and throw it a beat earlier, it must become a 4-beat throw. This 4 stays the same incidentally. And as I shift this 2 to the right and throw it 1 beat later, it must become a 1-beat throw. And there I am at my pattern 441. Next challenge, make a site swap to arrive at the pattern 531, which we saw over here. If you fancy giving that a go, pause the video now. Well done if you said that you need to swap the two 4s to arrive at 531. Indeed, as this 4 shifts 1 to the left and is thrown a beat earlier in time, it must be thrown as a 5. And as this 4 shifts to the right and is thrown a beat later, it must be thrown as a 3. The 1 stays the same, and tick, I have got my 531 juggling pattern. Great, so far we've seen how swapping the sites of two numbers in a juggable pattern can give us another juggable pattern. And now let us take a little look at some of the mathematical curiosities that arise when we do 4-ball or more ball juggling. Now if you've been to the circus, you've probably seen people juggling many more than 3 objects only. So the first question I want us to ask ourselves is, how can I work out the number of balls in a juggling pattern? And to demonstrate this, I've written 3 site swaps on the board. 531, 744 and 4413. This is the first site swap that we have seen whose period is equal to 4. The period is just how many throws are made before the sequence repeats itself. You can have 3-ball juggling patterns, period 4, not a problem, we just haven't seen them yet. So this 531, well, we already saw 531 and we know it's a 3-ball pattern. The way in which we can check how many balls there are in a pattern is by taking the mean average. The mean average of 5, 3 and 1 is very simply 5 plus 3 plus 1 divided by 3, which is 9 over 3, which is 3. So this is a 3-ball juggling pattern. What about the mean average of 7 and 4 and 4? 7 plus 4 over 3 is equal to 15 over 3. This is a 5-ball juggling pattern. And here we can see it in action. The 7 is the high crossing throw, and the 4s are the throws which are returning to the same hand. 7, 4, 4, 7, 4, 4, 7, 4. And finally, what about this 4, 4, 1, 3? Well, 4 plus 1 plus 3. This time I need to divide by 4 because there were 4 numbers. The period is 4. And I get 8, 9, 12 over 4. Indeed, this is also a 3-ball juggling pattern. So you should be able to see the 4s are the throws that return to the same hand, the 1 is the pass, and the 3 is the throw that switches hands. And a really interesting point to note here is that because the pattern has an even period, it always begins on the same hand, so the same hands always make the same throws, and therefore the green and blue ball never switch hands. In light of what I've just explained about the mean average being the number of balls in a site swap pattern, it's important that we don't fall into the trap of thinking that any 3 numbers or any list of numbers that have an average that is an integer, such as 432, which averages to 3, is a juggling pattern. Indeed, if I draw this on the ladder diagram, I can see that if I throw a 4 throw, 1, 2, 3, 4, I'm back here. Then if I throw a 3 throw from my left hand, 1, 2, 3, I'm here. And if I throw after that a 2 throw from my right hand, 1, 2, we have a very big issue. All of the balls land in the same hand at the same time. And therefore, even though 432 averages to 3, it is not a juggleable pattern. Here comes a really cool algorithm that we can use to check if a sequence of numbers is juggleable. So I've written 2 sequences on the screen. 432, which we've already seen above, is not juggleable, and 4413, which we saw earlier in the video, is juggleable. And so I need to generate a test sequence for each of these, and I generate that test sequence by writing the real integers beginning at 0 in ascending order under each of the sequences, and I add those to the sequence. So 4 plus 0 is 4, 3 plus 1 is 4, 2 plus 2 is 4, and over here I get 4, 5, 3, and 6. I look at the period. Over here the period is 3 because there are 3 numbers in the pattern, and over here the period is 4, and I must find the remainder when I divide this sequence of numbers by the period. So 4 divided by 3 leaves me with remainder 1. 4 divided by 3, remainder 1. 4 divided by 3, remainder 1. And over here I must do 4 divided by period, which is 4. So 4 divided by 4 leaves me with remainder 0. 5 divided by 4, remainder 1. Remainder 3, and remainder 2. And these are my test sequences. And long story short, if any number in the test sequence is the same, the pattern is not juggleable. So over here, all of the numbers are the same, and therefore the pattern is most definitely not juggleable. Whilst over here, all the numbers are different, therefore the pattern is juggleable. Now in this video, I'm not going to explain exactly why this algorithm works, but if you want a fun mathematical challenge, I recommend that you think about it. Here's a clue to get you started. In this test sequence down here, we had all the numbers the same, 1, 1, 1. And indeed, in this juggling pattern 4 through 2, all the balls arrived in the same hand at the same time. So there's a little food for thought to get you started on why this algorithm works, and good luck with it. Of course, being a physicist, I couldn't resist putting in a teeny weeny bit of physics into my Maths of Juggling video. So this is all about how high I should throw the balls. Now, if you study A-level physics or above, you should have seen Suvat equations, and it shouldn't be too much of a stretch for you to prove that the height to which a ball goes is proportional to the time it spends in the air squared. And therefore, if I would like to juggle a pattern like 531, and if I remember that this is the ratio of the times, i.e. the beats that the balls spend in the air, if height is proportional to time squared, the ratio of the heights should be the square of these ratios. And so indeed, to throw this perfect time ratio, I must throw the balls in this height ratio. For example, if I were to throw my 5-beat throw at a height of 250 centimeters, so about 2.5 meters, which is a reasonable height to throw it, then I'd better throw my 3-beat throw at 90 centimeters and my 1-beat throw at 10 centimeters. Now, by no means is Hysoj a perfect juggler, but if he were, the ratio of heights of the blue ball at the top of this freeze frame and the orange ball in the middle should be 25 to 9, as they are 5-beat and 3-beat throws respectively. And believe it or not, this is only the tip of the iceberg when it comes to the maths of juggling. For example, what's to stop me throwing 2 balls from the same hand at the same time? This is what we call a non-vanilla site swap or a multiplex pattern. Here is an example. That is a cool pattern. And what about if I throw with my right and my left hand at the same time in what we call a synchronous pattern rather than right, left, which is asynchronous? So in the notation for synchronous patterns, the curly brackets represents the fact it's synchronous. Inside the brackets we have right hand, left hand respectively, and the little X denotes the fact that the throw is crossing hands. Or, here comes an even wackier idea. What about if I join my long lost brother Hysoj, and together we have 4 hands, and we call up more friends, and we get n hands, and we have p objects, and suddenly we have n hands, p objects, and the permutations and the combinations get very crazy, very mathematically involved, very quickly. Let's return to normality for one moment with one juggler and his favourite site swap, which is 7, 4, 1. The average of these 3 numbers is 4, and so indeed it's a 4-ball site swap, but it's special in a different way. This is what we call an excited state, and all it means is to enter this repeating cycle of 7, 4, 1. I can't start with a 7, a 4, or a 1. Indeed, I must throw a 5-beat throw, and then I can enter this cycle ad infinitum. And this is what we call an excited state. Very closely linked to excited states of atoms in physics and chemistry. It's my favourite site swap pattern, so I'm signing out with this one over to Hysoj one last time. So here Hisoj is juggling the simplest 4-ball pattern, which is 4. He's going to throw a 5, and bingo, he's into the excited state 7-4-1. Let's catch that one more time in slow motion. So here we are, 4, 4, 4, 4, 4. There's the 5. Bingo, he's into the excited state.
And that's the master juggling.